Good morning, everybody. Hope you're all healthy and safe. We are going to move on to the second portion of our Hilbert-Schmidt theorem, which was in chapter 6 of self-adjoint operators. So in the previous lecture, we had started with the proof of Hilbert-Schmidt theorem, and we had proved that for any compact symmetric operators, we can always find a set of eigenvalues which satisfy a particular inequality, right? That is mod lambda 1 is greater than or equal to mod lambda 2, etc. And we had proved that with the help of the induction process, and now the remaining portion of this theorem, it is corresponding to this orthonormal system of eigenvectors. Okay, we have the following three things. That is, first thing, for every x element of the Hilbert space H, we have x is equal to y plus summation inner product x ei. Okay, where I is greater than or equal to 1, where y element of kernel of T. That is, any element in the Hilbert space can be expressed as the sum of an element in the kernel of T and as sum of inner product x ei into ei, where ei forms the orthonormal system of eigenvectors. Second one, it is easily derived from the first point, that is T of x will be equal to summation inner product T of x ei and which is further equal to summation lambda I inner product x ei. Okay. And the third one is this particular set actually forms an orthonormal basis of the image of T. So all these three are interlinked. So just keep in mind what we have to prove. First of all, we have to prove that any element can be expressed as of the Hilbert space can be expressed as the sum of an element in the kernel of T and sum of inner product x ei into ei. And correspondingly we can find the value of T of x, and also we can prove that the set ei forms an orthonormal basis of the image of T. Now the second one is clear from the third one is clear from the second point, because you can see that T of x is written as lambda I into inner product x ei into ei. That is all this thing, if you consider it as when treated as a constant term, it is actually the linear combination, or this is considered as scalars. It is actually the linear combination of set of ei, right? It is a linear combination of elements in ei. So any element in the image of T of x, we are writing T of x is equal to, suppose T of x is some value, say v, then v is equal to T of x means v is a linear combination of elements of ei. So clearly ei forms a orthonormal basis of image of T. So the third point is clear from the second expression itself. So we shall move on to the proof of the first portion, that is how we can express an element in the Hilbert space with the help of these eigenvectors. For any x element of H, let xn is equal to let xn is equal to summation I equal to 1 to n inner product x ei. And one more thing that we are assuming, yn is equal to x minus xn. So these two things we are assuming, that is, for any x in the Hilbert space H, xn is of this form, that is xn is equal to summation I equal to 1 to n inner product x ei, and yn is x minus xn. Okay, now then if we express yn as x minus xn, then we can say that yn is an element of en orthogonal. How can we say that? Now, how did we assume en to be? En was supposed to be the span of set of ei's, right? I greater than equal to 1, or I is equal to 1 to n. So yn is an element of en orthogonal, where en is a span of set of ei. So how can we prove that? Let's see how is the statement true. Now let us take yn and an element of the span of that set, say EG. right? We need to show that the inner product of yn and ej is 0, then yn will be an element of en orthogonal. So this can be written as yn was assumed to be x minus xn into ej. Now let us write what was xn. Xn was summation inner product x ei comma ej. So let me just write it out. This will be inner product x ej minus, this is the constant, so summation inner product x ei into ei ej, right? So when will this value be? No, since it is an orthonormal system, this will form this will be 0 except for when I equal to j, right? So this will be nothing but inner product x ej minus, all other terms will be 0, so it will be again x ej. So this will be equal to, when I is j, this value will be 1, all other terms it will be 0, so this is nothing but 0. Therefore yn is, you can say it is orthogonal to set ej, or yn is an element of en orthogonal, as en was span of this set. So yn is an element of en orthogonal. So I hope this much is clear. Now, as yn belongs to en orthogonal, we have t of yn can be written as tn plus 1 of yn. Now why is that? Because if you remember in the theorem, we had tn plus 1 was nothing but the operator t restricted to en orthogonal, right? So yn is an element of en orthogonal, so whenever t acts on an element of en orthogonal, it is same as tn plus 1. So this is tn plus 1. Now if you remember, we had stopped the last proving the first portion of the theorem by considering two cases, right? First case was that tn plus 1 is 0, and the second case was, it was the set of lambda I, that is the eigenvectors, is infinite. These were the two cases. So here also we'll be considering these two cases. So in case A, what happens is tn plus 1 is 0, so this implies, what can I say, tn plus 1 acting on yn will also be 0, and therefore t of yn will be 0, right, from the statement. T of yn is 0. So if t of yn is 0, I can say that yn is an element of kernel of t, right? And how did we express yn? Yn was nothing but x minus xn, right? So this implies x is equal to yn plus xn. And how was xn? Xn was summation. So if you just recall, the first thing that we have to prove in today's section, or in today's theorem, is that every element of the space H can be written as the sum of an element in the kernel of T. We have seen that yn is an element of kernel of T, sum of an element in kernel of T plus summation inner product x ei. So xn is nothing but inner product x ei. So first case we have proved it. Now let's see the case B, that is when the set is infinite. In case B, set of eigenvalues is infinite. So by the property 5-point proposition, sorry, not property, proposition 5.2.4, that was something which we did in the previous chapter. We can say that, we can say the set sequence lambda n, it will tend to 0. That was because we had said that the set of eigenvalues for a symmetric compact operator is always finite, Okay, so in this case, if it is infinite, we can say that, and we had considered that lambda I was greater than or equal to epsilon I. Okay, proposition 5.2.4 was the set of eigenvalues was finite and mod lambda I is greater than or equal to epsilon I. So here, if you are considering the set to be infinite, then this will not be true, that is, this will be less than or equal to epsilon I. So we can say that the sequence, it tends to 0. Okay, that is how we are using the proposition 5.2.4 here. So therefore, what we are going to get is norm of t of yn is nothing but the same as norm of t restricted to en orthogonal of acting on yn. Why? Because yn is an element of en orthogonal. This is less than or equal to, I can say, norm of t restricted to en orthogonal into norm of yn, right? And norm of t en orthogonal, by our theorem, it is nothing but norm of t n plus 1 into norm yn. Okay, and by our theorem itself, this is nothing but mod lambda n plus 1 into norm yn. Now lambda n is a sequence which is tending to 0, so I can say that norm t of yn tends to 0, where yn is an element of en orthogonal. Okay, so now let's move on to the term yn. Okay, we have yn is equal to x minus xn. So therefore, limit n tending to infinity yn will be equal to limit n tending to infinity x minus xn. So I can write this as x minus limit n tends to infinity xn, right? Now what was xn? Xn was, let me just write it down, xn was nothing but limit inner product limit n tends to infinity inner product summation I equal to 1 to n x ei. This was xn. So this will be actually nothing but x minus, so this is equal to x minus x dash, where x dash is nothing but summation I equal to 1 to infinity. As n tends to infinity, this becomes 1 to infinity inner product x ei. Now how can we say that the confirmation of this limiting value exists by corollary 2.1.5. So if you just refer to this corollary, you can say that for any x, we can always find an element x dash, such that x dash is expressed as this form. So this limiting value actually exists, right? So I'm going to call this x minus x dash equal to y. I'm just going to rename it. So the limit of yn exists. Okay, now so as limit of yn exists and it is considered to be y, I can say that norm t of yn tends to norm t of y, right? But we have just now seen that norm of t of yn is actually tending to 0. So these two should be equal. So this implies norm of t of y is equal to 0, which implies t of y will be equal to 0, and hence y is again an element of kernel of t, right? Y is an element of kernel of t. Therefore, x minus limit n tending to infinity xn will be nothing but limit n tending to infinity. This we have just now seen, right? Yn is x minus xn, so if I apply limit on both the sides, I get x minus limit n tends to infinity xn is equal to limit n tends to infinity yn. That is, limit n tends to infinity xn is nothing but I is equal to 1 to infinity inner product x ei. Okay, and this is y, where y is an element of kernel of t. So again you get the same expression, that is x is equal to any element in the Hilbert space. X can be written as sum of an element in kernel of T and summation inner product x ei ei. Okay, so this is about our first part, how we can express an element as the sum of an element in the Hilbert space, kernel of that operator, and the summation. Now we have to show what is the value of T of x, right? Okay, this is the second point that we are proving. Okay, we have just now seen that x is nothing but y plus summation I equal to 1 to infinity inner product x ei ei. So let's apply tx t on both the sides, right? So this is y plus summation I equal to 1 to infinity inner product x ei ei. So I can write this as t of y plus t of or I can take the summation out common, I is equal to 1 to infinity inner product x ei into t of ei, right? So t of y is 0y because y is an element of kernel of T. So this is 0 plus, and what is t of ei? T of ei is nothing but, I can write it as lambda I, right, into ei. So this can be written as I is equal to 1 to infinity lambda I into inner product x ei into ei, because T of ei is equal to lambda I ei. It is the eigenvector. So I get T of x is equal to summation I equal to 1 to infinity lambda I into inner product x ei ei. Now as any element in the image of T is expressed as a linear combination of set of ei's, that is the eigenvectors, we can say the third point also, that is the set of eigenvectors forms an orthonormal basis of image of T, right? So I hope the proof of this Hilbert-Schmidt theorem is clear. So we have seen how we can express an element of the space of the Hilbert space as an element of as a sum of an element in the kernel of T and sum of inner product x ei ei, where set ei forms an orthonormal basis, and with the help of that we have expressed T of x also in terms of ei, and also we have seen that the set ei forms an orthonormal basis corresponding to the orthonormal basis of which image of T. So that's it for today's class. Thank you all.